Here we discuss some results from congruences and some of the problems using these results. Already we have a result that if A is congruent to B mod M and if C is any number, then AC is congruent to BC mod M. For example, if you take 8 is congruent to 3 mod 5, so 16 is congruent to 6 mod 5. 8 minus 3, 5 is a multiple of 5. 16 minus 6, 10, that is also a multiple of 5. So if 8 is congruent to 3 mod 5, it is very clear that 16 is congruent to 6 mod 5. Now what about the converse of this result? That is, if AC congruent to BC mod M, can we say that A congruent to B mod M? Let us take an example. We know 40 is congruent to 4 mod 12 because 40 minus 4 is 36 is a multiple of 12. Now 40 and 4 you can regard as 4 into 10 and 4 into 1. So this is 4 into 10 congruent to 4 into 1 mod 12. Now we expect that 4 is cancelled here. What do we get? We should get 10 congruent to 1 mod 12. But it is not. 10 is actually not congruent to 1 mod 12. And therefore this example shows that if AC congruent to BC mod M, it doesn't mean that A congruent to B mod M. You can take another example. We know that 8 into 37 is congruent to 8 into 7 mod 12. Because 8 into 37 you find, then minus 8 into 7, you can see that it is a multiple of 12. Now cancelling this 8, you expect that 37 is congruent to 7 mod 12. 37 minus 7 is actually 30. 30 is not a multiple of 12. So actually 37 is not congruent to 7 mod 12. Even if 8 into 37 is congruent to 8 into 7 mod 12, here 37 is not congruent to 7 mod 12. So you cannot cancel this C as we like. So if AC congruent to BC mod M need not imply A congruent to B mod M. That is the congruence that we get after cancelling C. So under what condition this is true, that we see through one theorem. The theorem is this. If AC is congruent to BC mod M and CM equal to 1, then A is congruent to B mod M. CM means GCD of C and M is 1. So if C and M are relatively prime, that is the multiplying factor C and this M are relatively prime, then that factor C get cancelled. That is, A is congruent to B mod M. So let us go for the proof of this theorem. Given AC is congruent to BC mod M, which shows that M divides AC minus BC. That is, M divides C into A minus B. So M is actually dividing the product of C and A minus B. But M and C are relatively prime. That is, M cannot divide C. So the only possibility is that M divides A minus B only. So this implies M divides A minus B, since MC is equal to 1. That is, GCD of M and C is 1. M and C are relatively prime. M can only divide A minus B. That is, M divides A minus B means, that is, A minus B is equal to some Km for some K. That means A is congruent to B mod M. So if AC congruent to BC mod M and C is such that C and M are relatively prime, then A is congruent to B mod M. Now, see one example like this. We have 78 is clearly congruent to 48 mod 5. 78 is congruent to 48 mod 5. Because 78 minus 48 is 30, it's a multiple of 5. And 78, 48 you can write respectively as 6 into 13, 6 into 8 mod 5. Here this factor C and 5 are such that 6, 5 is equal to 1. GCD of 6 and 5 is 1. That is 6 and 5 are relatively prime. So this factor 6 and M, that is 5, are relatively prime here, and therefore by the previous theorem you can cancel 6. We get 13 is congruent to 8 mod 5, which is true. 13 minus 8 is actually 10, is a multiple of 5. So if we can factorize the two numbers A and B like this, and one of the factors, if it is relatively prime with this M 5, then you can cancel that factor. So this is what this example shows. Now we have another theorem. If AC congruent to BC mod M, and suppose C and M are not relatively prime, that is GCD of C and M is D, then A is congruent to B mod M by D. That is the result that we have. Let us go for the proof here. The theorem is telling that if AC congruent to BC mod M and GCD of C and M is D, then we have to prove A is congruent to B mod M by D, M by GCD of C and M. Since AC congruent to BC mod M, M divides AC minus BC. That is M divides C into A minus B. Now divide by D. M divides C into A minus B means actually C into A minus B is equal to some Kn for some K in Z. Now divide by D. That is C by D into A minus B is equal to K into M by D. Since C and M are such that Cm is equal to D, that is GCD of Cm is equal to D, then GCD of C by D, M by D is 1. That is C by D and M by D are relatively prime. So these two factors come here, C by D and M by D, and C by D and M by D are relatively prime, and at the same time C by D into A minus B is K times M by D, and therefore this shows that M by D divides A minus B. That is M by D divides A minus B. That is A is congruent to B mod M by D. So we have the result that AC congruent to BC mod M and Cm is D, then A is congruent to B mod M by D. Now we have another result that if A is congruent to B mod M1, A is congruent to B mod M2, etc., A is congruent to B mod Mk, then A is congruent to B mod LCM of M1, M2, etc., Mk. So let us go for the proof here. Given A is congruent to B mod M1, which implies M1 divides A minus B. A is congruent to B mod M2, which implies M2 divides A minus B, etc. A is congruent to B mod Mk, which implies Mk divides A minus B. So here all the integers m1, m2, etc. mk divide a minus b, and therefore LCM of m1, m2, etc. mk also divides a minus b, and therefore a minus b is congruent to 0 mod m1, m2, etc. mk, and that is written as A is congruent to B mod m1, m2, etc. mk. So we have the result that if A is congruent to B mod m1, A is congruent to B mod m2, and so on, A is congruent to B mod mk, then A is congruent to B mod LCM of m1, m2, etc. mk. Now this is illustrated by this problem here. Here we know 197 is congruent to 77 mod 6. 197 is also congruent to 77 mod 10. 197 is congruent to 77 mod 15. And therefore by this theorem 197 is congruent to 77 mod LCM of 6, 10, 50. That is 197 is congruent to 77 mod. We know LCM of 6, 10, 15 is 30. So 197 is congruent to 77 mod 30. Now there is a result that we can derive from this previous theorem. If A is congruent to B mod m1, A is congruent to B mod m2, etc. A is congruent to B mod mk, where the moduli are pairwise relatively prime, then A is congruent to B mod the product of m1, m2, etc. mk. So the given here A is congruent to B mod m1, A is congruent to B mod m2, etc. A is congruent to B mod mk. So by the previous theorem we have A is congruent to B mod LCM of m1, m2, etc. mk. But here mi are such that they are pairwise relatively prime. That is the mi mj for I not equal to j is such that GCD of mi mj is 1. So in such cases we know the GCD of relatively prime numbers are the product of the prime numbers. So A is congruent to B mod the product of these moduli, that is m1 into m2 into etc. m into k. Since the GCD of m1, m2, etc. so the LCM of m1, m2, etc. mk is the product of m1, m2, etc. mk, since they are relatively prime to one another. So we have the result. If m1, m2, etc. mk, the moduli are relatively prime, pairwise relatively prime, then A is congruent to B mod m1, m2, etc. mk. Now we have many problems in exercise under this section. One of the types is that rewrite the sentence given using congruence relation. congruence relation. Using congruence relation, how to write some sentences. So this is given here. The first sentence is like this. N is an odd integer. N is an odd integer. We know an odd integer is a number. When it is divided by 2, it leaves the remainder 1. So this can be written by using congruence relation as n, that is the number. It leaves the remainder 1 on dividing by 2. So we can write this relation as, or this sentence n is an odd integer as n congruent to 1 mod 2. Similarly, n is an even integer. We know even integer is a multiple of 2, or it leaves the remainder 0 when on division by 2. So n is congruent to 0 mod 2. Similarly, if suppose n is a multiple of 5. N is a multiple of 5. So this can be written as n congruent to 0 mod 5. So this is the way some of the sentences like odd integer, multiple of 5, etc. can be written using congruence relation. There are some problems that we are using in our daily life and which can be solved by using congruence relation. For example, one of the problem is like this. If today is Tuesday, what day it will be? In some 129 days. That is, after 129 days, what day will be? We have to find out. Today is Tuesday. So after 1 day it will be Wednesday. After 2 days it will be Thursday. After 3rd day it will be Friday. It goes on like that. Then after 7th day it will be Monday. Tuesday. Then 8th day again it will be Wednesday. It goes like this. So what does it show? This shows that actually to find the day after 129 days, it is concerned with the congruent modulo 7, because after 7 days the day repeats. So to find the day, you have to find 129 congruent to modulo 7. That is what is the least residue of 129 congruent modulo 7. So here find actually the least residue of 129 modulo 7. So on division, when you divide 129 by 7, you can see that it is 7, then 59, then 8 you will get. 8 into 7 is 56 by 3. So the remainder is 3. So the remainder is 3 means it is Friday. Since the remainder is 129 is congruent to 3 mod 7, it indicates that that day is Friday. So the day is Friday. Now another problem is that if it is 9 a.m., if it is 9 a.m., now what time will it be? What time will it be in 1900 hours? In 1900 hours. If it is 9 a.m., what time will it be in 1900 hours? Now we know that after this 9 a.m. repeats after 24 hours. So by 24 hours the 9 a.m. comes. So in order to find what time will be after 1900 hours, you need to find only 1900 modulo 24. That is the least residue. Find the least residue of 1900 modulo 24. Now we just find 1900 divided by 24. You just find. You can see that 190 it goes 7 times. 7 into 24 is 168. On subtraction you get 22. Then 220 it goes 9 times. So 9 into 24 is 216. So we are getting 4, the remainder. That means 1900 is congruent to 4 mod 24. And therefore, now it is 9 am. So 1900 congruent to 4 mod 24 means the time is 4 am. 4 am. Suppose we get the remainder as some 21. Suppose on division by 24, suppose we get 21. Then the time is 9 pm. 21 hours means actually it is 9 pm. Now let us see another problem. Find the last 2 digits in the decimal value of. Find the last 2 digits in the decimal value of 1776 raised to 1976. You know that the last 2 digits is obtained by finding the remainder when divided by 100. We know 1776 is congruent to 76 mod 100. That means 1776 when it is divided by 100, it leaves the remainder 76, means the last 2 numbers are 76 we are getting. So 1776, we want to find the last 2 digits in the decimal value of 1776 raised to 1976. Now you consider the number 1776 raised to 1976. It is clearly congruent to 76 raised to 1976 mod 100. You know, 76 raised to n, if you find for any n, it is for example 76 square, 76 cube, it ends in 76 when n is odd, even, because 76 into 76 is 76 into 76. If you find, you can see that ends in 76, whether n is odd or even. 76 into 76 into 76, again you can see that ends in 76. That means 76 to the power of n ends actually in 76 always, and therefore it is congruent to 76 mod 10. Similarly, to find the last two digits in the decimal value of 1829 raised to 1829. So this is one problem, this is another problem. You have to find the last two digits in the decimal value of 1829 raised to 1829. We know 1829 is congruent to 29 mod 100. Therefore, we have to find the 29 raised to 1829 mod 100. 29 raised to n for an integer n. You can see that it is congruent to 41 mod 100 if n is even, is congruent to 89 mod 100 if n is odd. So if the power n is an even number, it is congruent to 41 mod 100. Whether if it is odd, then 29 raised to n is congruent to 89 mod 100. So here 1829, we have to find the power 1829 raised to 1829 is congruent to 29 raised to 1829, and this n here 1829 is an odd number, and therefore this is congruent to 89 mod 100, and therefore the last two digits in the decimal value of 1829 raised to 1829 is 89. Last two digits is 89.